Last topic in chapter 7, we want to return to the idea of molecular shapes and talk about the shapes of molecules with expanded valence. So I'm going to say right now the purpose of this is just to provide a little bit of context, especially in relating these, most importantly, relating these to the earlier shapes we've learned. We are going to touch on some shapes of some of the more exotic, but we don't really necessarily need to be focusing too much on those. We're going to touch on them, but mostly focus on shapes that we've learned previously of some of these expanded valence and unfilled valence molecules. The VSEPR ideas that we previously learned about for determining shape still apply to molecules that don't follow the octet rule. Electron pair geometry is just based on the number of electron groups. If there's 2, it's linear. If there's 3, it's trigonal planar. If there's 4, it's tetrahedral. Once we move into expanded valence, it's possible to have 5 or 6 electron groups, and those have their own associated electron pair geometries called trigonal, bipyramidal, and octahedral, respectively. So for 5 electron groups is trigonal bipyramidal. This is the arrangement that if you have 5 things, this is what they'll form. The name comes from the fact, so trigonal is this, 1, 2, 3. Those 3 atoms are in a plane, so they are flat. And then bi is 2. And the pyramidal, there's 2 pyramids. Basically, there's a pyramid going up, and then there's a second pyramid going down. So those are the bi-pyramids. So you can imagine this is 2 pyramids, 2 trigonal pyramids that are like jammed together at their base. So PCl5 is a trigonal bipyramidal molecule. It has a nice arrangement. This is if you have 5 things and they need to spread out, this is what they look like. This gives you a 3-dimensional representation. You can see that there's like the 2 parts that are going out to the pyramid are sticking up in opposite directions. They're in a straight line. And then the other 3, you can see then are forming this sort of planar shape. And so this is a trigonal bipyramidal shape. You can see it moving around in fancy 3D. We can see a nice kind of depiction. Again, those ones, there's this kind of the 2 that are sticking up, they're linear, whereas the other 3 are forming that trigonal planar bit. If you have 6 groups, that's called octahedral. This is similar to tetrahedral. It's the name of the shape. If you have a shape, you'll note, let's see if I can trace it out. You have a bunch of triangular faces formed from all of these pairs. I'm gonna not try to butcher it too bad, but that is an octahedral. This is not, yeah, that's an octahedral shape. So it's a 3-dimensional shape. It's similar to a tetrahedron. The octahedral is a reference to the 3-dimensional shape traced out by the atoms. It is not the atoms are the corners of. It's not a reference to the arrangement of the atoms themselves. If we want to look at it in 3 dimensions, basically what we can see is it's just all a bunch of right angles. So it's basically 3 pairs of atoms that are across from each other. So it's similar to like coordinate system. So like a 3-dimensional coordinate system, an X, Y, and a Z axis. That is what we're looking at here, where they're all going in the different directions. So with those electron pair geometries, there are also shapes. I'm going to tell you right now, we're going to talk very briefly about these. I do not expect you to know all of these shapes. There are 7 of them. There's a lot of them. We're just going to look at them just to kind of look at the flavors of these expanded valence shapes. But I do not expect you to, but you could, it follows, the VSEPR theory still applies here. It still just becomes the same idea of number of electron groups and then number of lone pairs. And that tells you what the shape is. It's all the same idea. Just because these molecules are more exotic doesn't mean the underlying physics is changing. It's still a bunch of negatively charged electrons that want to stay away from each other. So when you have 5 groups, electron pair geometry that's trigonal bipyramidal, there are 4 possible shapes based on having 0, 1, 2, or 3 lone pairs. PCl5 is an example. That's a trigonal bipyramidal shape. Just like previously, when there's 0 lone pairs, the molecular shape matches the name of the electron pair geometry. 1 lone pair gets you a seesaw representation, which that's literally because it looks like a seesaw. This being kind of where one person would sit, and this is where the other person would sit. Then when you have 2 lone pairs, it's called T-shaped, and 3 lone pairs is once again called linear. So that's a reuse of a name from earlier because the atoms are arranged linearly. These shapes kind of show, again, the purpose of the shape names is to be descriptive. It's either highly geometric, like trigonal bipyramidal, or it's a reference to a common object like the letter T or a seesaw. If you have 6 groups, 0 lone pairs is octahedral, like SF6. Bromium pentachloride has 1 lone pair. That's called square pyramidal. That's a reference to the fact that these atoms form a square. And then this would be the top of the pyramid. 2 lone pairs gets you square planar. Xenon tetrafluoride has a square planar. They're all flat, so we've seen planar before, but this time the outer atoms trace out a square. So that's why we get square planar there. And so we have all sorts of new shapes that come from this. Again, the purpose here is just to show you that there is the rules that we've seen previously still work. We're not going to worry about, say, applying these shapes. What we do want to focus on is being able to apply the rules and the shapes we learned previously to molecules with atoms that violate the octet rule, because the same process that we used previously is still going to apply. So for example, phosphate. So PO4 3-, if we look at our Lewis structure, that phosphorus atom is associated with 10 electrons. It has the 1 double bond and the 3 single bonds. But when we're going about figuring out what the shape is, we don't care that it violates the octet rule. That never mattered. We would look at it and count how many outer atoms does the central atom bonded to, and how many lone pairs does it have. 4 outer atoms, 0 lone pairs on that phosphorus. There are 4 directions. So it has a tetrahedral electron pair geometry still, and it has a tetrahedral shape because there aren't any lone pairs. So if we look at the 3-dimensional structure, it's the same tetrahedral shape we've seen previously. When we were looking at atoms that followed the octet rule, it didn't matter. We didn't care that they followed the octet rule. We never were counting how many electrons were anywhere. How many things were they bonded to and how many of them were in lone pairs is what we actually care about. So we can still get the same shapes for these expanded valence as long as they don't have too many bonds. Beryllium dichloride. That beryllium does not follow the octet rule. It only has 4 electrons in its valence, which is expected for a beryllium atom. And so when we're going to figure out the shape of the molecule, we look at the beryllium. How many outer atoms is it bonded to? 2. How many lone pairs does it have? 0. So that means this thing's going to have a linear electron pair geometry and a linear shape, which beryllium dichloride as a molecule does, right? It has this nice shape where we can see the beryllium's in the middle, it's a very small atom, and the chlorines, the big chlorines, are out in a straight line. So this is overall a linear molecule. The Vesper rules don't change here, just because the beryllium doesn't have only has 4 electrons. Boron trifluoride. That boron only has 6 electrons, expected for boron atoms. But we want to figure out the shape. It's bonded to 3 outer atoms, 0 lone pairs. That's going to be a trigonal planar shape. We know there's 3 directions. They're going to spread out in their 3 directions. Here is the trigonal planar structure for boron trifluoride. This is actually characteristic of boron, right? If we think boron always tends to form 3 single bonds and have no lone pairs, boron atoms are almost always trigonal planar, especially in molecules where they're not doing any sort of fancy coordinate covalent or anything like that. They always have 3 bonds. They never follow the octet rule, and they're always flat. They're always trigonal planar. Those are really good kind of associations with boron. Xenon trioxide. So when we want to figure out its shape, xenon is the central atom. It's bonded to 3 outer atoms, and we can see it has 1 lone pair. So this would have a tetrahedral electron pair geometry, but there is a lone pair in the central atom, so that means it has a trigonal pyramidal shape. So xenon trioxide is going to look something like this. This is a pretty gnarly structure, right? That xenon is associated with what? 4, 8, 12, 14 electrons. So there's a lot going on there with the xenon. There's a lot of electrons, but xenon is also huge. It is near the bottom of the periodic table. It can accommodate a lot of bonding. And so that's why you have this. You know, it can really kind of grow out and really accommodate this. You got a bunch of oxygens that want to form bonds. Xenon can do a lot of bonding. It's got a lot of electrons. And so, but we can see the shape follows the same rule. The Lewis structure looks kind of nutty. This is a pretty nutty molecule. But the shape follows not nutty rules. Chapter 7. It's a long one. Bonding, all the way back with that, into molecules, drawing Lewis structures, everything like that, and then kind of some of this, the shape, three-dimensional stuff, and then all these octet rule exception ideas, what we want to be familiar with coming out of chapter 7. So really kind of understanding bonding, why bonds happen, coming up with molecules, analyzing those molecules and their shapes, and then kind of talking about some weird things that maybe violate some of those rules we learned all about earlier in the chapter. Okay, that is it. Participation 626, 4 questions. You want to find all 4 of them, get them answered, get those answers submitted over on Blackboard. It was a front-heavy set of videos as far as where the participation questions were found. Homework on Saturday over on Active. Participation answers go live Friday night. Check those out. Otherwise, that's it for this week. Next week, week 5, last week of the class. So we're going to start to see those kind of end of the term assignments. The lab technique presentation is going to be due, and then we'll do our final exam on that Thursday. We will still have a Monday, Tuesday set of videos, and we'll do some lab activities on Tuesday. There's a pre-lab, no notebook. If you have any questions about anything, let me know. Otherwise, enjoy your weekend. Bye-bye.